So I'm recording the lecture the same way as I did last week. I don't have another microphone or something, but it's something I'm looking into. I saw a bunch of people watch the online lecture, and I know, yeah, the audio is pretty bad. Hopefully it's at least comprehensible, listenable for an hour or so, but I will try my best. All right. So your first quiz is next week. For this class, it will be starting right at 9 o'clock, so the beginning of class. Make sure you're here a little bit before then if you want the full time to work on your quiz. Here's the iClicker code, just if you want to enter that in real quick. We're going to have clicker questions again, but they are not graded. I don't look at attendance or anything in any way. It's just a way for you to participate and for me to see how we're doing throughout the lecture. So problem starts. If you saw, I posted those on Canvas along with a bunch of practice quizzes. The 5 practice quizzes I did not make. Those are just from a previous quarter, and they do not necessarily reflect the difficulty of the quizzes that I will give. My intention is to make my quizzes a little bit easier. Intention. You know, we're all working on it. If I err on that, the curve will make up for it. But yeah, though if you are comfortable with those practice problems, the quiz should be manageable. The problem starts, as you saw, are 4 setups for a problem. I don't ask any questions, but just kind of give the diagram and a little description of what's going on. Your quiz will come from one of those. So the exact same thing, that paragraph and the diagram will be on your quiz, I will add to it a couple of things like questions for you to solve. The idea is that you shouldn't be caught off guard on the quiz. I think it's a really important skill to be able to take a setup and then apply the model that we learned in class to it to try to solve its behavior. But I understand that can, I don't know, I'd like you to have some time with that. So definitely take a look at these. If you have very little time, just take 5 or 10 minutes. I really recommend just read through them, make sure things make sense just as far as what's happening in a problem. But you could go as far as writing out the equations, seeing what types of questions I could ask. Make up questions for yourself. Say, okay, what if I know this resistance of this pipe is this number? I know the E pump is this, whatever. What if I want to solve for the current? Something like that. But you can experiment all you want with these. Ask me questions, ask your TA questions, talk about them with each other. Anything short of really sharing numerical answers to questions you write for yourself. So, if you have like a fully worked out, detailed equation solution to something, don't post that on Piazza or stuff like that, but feel free to discuss them. That's why I put them up, for you to work on them and be as prepared as you can for the quiz on the day of. The reason being, I think the thing that's missing from like the 7B setup is like a graded homework. I really don't like that so much of the weight of the course is on in-class, like high-pressure assessments, like your quizzes and your final. I didn't want to add like homework sets because you already have plenty of work to do with the FNTs and stuff, and you don't get a ton of credit for them. So this is just a way to give you a chance to take some of that pressure off and outside of the classroom. So I encourage you to take advantage of it. We'll see how they work. If it's not really having much of an effect or you don't like them, we can change that, but I want to try them for at least the first 2 quizzes. I'm really open to feedback on this and anything in the course, so please don't hesitate to let me know what you think's working and what is not, even if that is an anonymous Piazza post, something like that. I want to know so I can do better later in the quarter. Okay, questions about problem starts. I will definitely be talking about them in my office hours on Mondays, and yeah, feel free to bring those to other TAs as well. All right, so this is where we ended last time with the complete Bernoullis equation. So the right-hand side, pressure, potential energy density, and kinetic energy density, or more specifically changes in each one of those things, happen just between 2 points. Right? We have a point A and a point B, and we only care about the values of each one of those things at the 2 endpoints. It doesn't matter what happens outside of that or in between them, just the values at the 2 endpoints. And that is what the delta is, right? It is a change in space from one point to another. There's no change in time because these are steady state. It's constant throughout time. So yeah, that's what the delta means. And these are all energy densities. not just joules, it's joules per unit volume, or Pascal, energy density. We don't care how big a system is, we just care about its behavior, and energy density will give that to us. The right side of the equation, E pump and minus IR, or resistance, or thermal dissipation, those are kind of like our external energy inputs, or things that take away from energy. Those are on the right side, and they only are important when they're in between our two endpoints. Right? You don't have a pump like you don't care about a pump like at the endpoint and outside of it. It matters in between point A and point B. So you can think of those as like external things to this system. You have a fixed amount of energy that you're spending on pressure, potential, and kinetic. Those things exchange all throughout a circuit, and the only way that total can change is if a pump gives more energy density or a pipe with resistance takes energy density away, transfers it to thermal energy, it dissipates it. This diagram here just kind of shows that. We have 3 values on the left, 3 values on the right for pressure, potential energy density, kinetic energy density, and E pump and minus IR in the middle. Questions on Bernoullis equation, because this is pretty much everything you need for the quiz, first of all. You do need continuity, so applying this, having like I1 equals I2, or like current throughout a whole circuit is continuous and the same, it's conserved, and also what current is, right? Our area times our speed, like A1 V1 equals I1. Those little things are also important, but this equation really does everything. If you're comfortable with that, you're good for the quiz. We will be moving on past it, though. So most of today's lecture is not relevant. Well, it could help, but you will not be quizzed on next week. All right, so let's look at an example, drinking through a straw. The purpose of this example, it's not, we have to make a lot of very simplifying assumptions, but it's just to take a system that looks, I don't know about complicated, but like something that it looks weird, not like a lot of the pictures that we've seen up on the board, the diagrams we've seen that we apply Bernoullis equation to, and see how we can fit our model to it, which I think is a really important part of this course. Again, the physics, you need to know them, certainly in this course, but probably going to forget at least a lot of it, and I think the real important thing that you can take from this class is how to problem solve like this and apply models that you do know to try to solve questions. So what's happening when water flows up through a straw? Why does that happen? So before you have a straw, before sucking on the straw, the surface of the water is at atmospheric pressure, right? It's in contact with the air, equal pressure, the water level's not moving. If you dove deeper down into the water, the pressure increases, right? But at the surface, it's atmospheric pressure. If I add a straw, nothing really changes, right? Before we suck on the straw, if I put the straw in, the water level remains constant, even in the straw, because there's nothing to change the pressure, and it's still a very simple scenario. PATM everywhere above the surface of the water. But now, what if we put our mouth on the straw and suck through it? Water flows up through the straw. So we're kind of making a simplifying assumption here, that being the kinetic energy density we're going to ignore. There is clearly flow through the straw, right? And when you drink through a straw, the water level in the cup goes down, right? There's not an infinite amount of water. But we're going to kind of look at this at like the instantaneous level. So just like the millisecond right after you start sucking on the straw, what's happening. So we'll just say we ignore like the real flow of water, the kinetic energy density. I just want to look at changes in pressure and potential. So it is a big simplifying assumption. What can you do? So now PATM still at the surface of the water, right? They're still at the same height, the surface of the water in the straw and outside. So the pressure is going to be the same, atmospheric pressure. But if we climb up through the straw, we have a change in potential energy. Between where? Our delta is from the surface to the mouth. The reason I picked those 2 points is just because, well, the surface of the water is a nice easy one. It's at atmospheric pressure, roughly, in this assumption. And yeah, the mouth is where it's going to. So we want to see, why does water flow out of the cup from the surface into our mouth? So let's look at Bernoullis equations. Like I said, we're going to ignore kinetic energy because we'll just say it's right when this is happening. We'll not really consider flow yet, and then there's no pump in between the surface of the water and our mouth, right? It's just an empty straw, and we'll ignore resistance. So we're just left with a change in pressure between the surface of the water and our mouth, and the change in potential energy density between those 2 points. So if we're going from the surface of the water to our mouth, our delta T is going to be our final minus initial, and that's going to be equal to negative rho g delta H. So I just took my delta P over volume, which is rho g delta H, and moved it to the other side. And then if I move atmospheric pressure over there, my nice simple answer is that the pressure of the water that's reaching our mouth is equal to atmospheric pressure minus some value that has to do with the height. Right? So the water entering our mouth is at a lower pressure than it was when it left the cup, which makes sense, right? You dive deeper underwater, higher pressure, you swim up toward the top, which, it's in a confined straw, but we're still going up. So if our potential energy is our potential energy is increasing, we're spending that pressure and our pressure decreases. So another way to think about it is that, so P decreasing from lower to higher, sucking in the air reduces the pressure in the straw, and water wants to flow from high pressure to low pressure. Right? That's something we'll talk a little bit more about next lecture, things flowing from high to low, and like high energy to low energy. And if we introduce like a lower pressure, a lower energy density in the straw, that point of contact right at the surface, where it used to be, it is air until we suck on it, at that point of contact, before we suck on the straw, the pressures are equal, right? That's why the water level's not moving. If you're pushing on each other equally as hard, the water level's constant. But if we reduce the pressure that's pushing down, the pressure from the water is going to win, right? The pressure of the water is still at atmospheric pressure because it still has the atmosphere pushing down on this water level. So if we reduce what's pushing down on it, the water level goes up. The water flows through the straw because we decrease the pressure inside of it. So the water flows from high pressure to low pressure in our mouth. We can also expand this model a little bit to kind of complete the circuit. Let's move it further into our mouth and then say at some point it reaches atmospheric pressure, right? Which is kind of the case. Our stomachs, I don't know exactly if this is true, but it's close to atmospheric pressure, right? Unless you really have to burp like full of air or something like that. The water is eventually going to reach atmospheric pressure. It's not going to be like negatively pressurized or anything inside you. So once we suck it up from the straw, it then somehow gets back to atmospheric pressure. And I think a very simple way to explain that is think of the mouth as a pump oriented inward. So if we put a pump there, then we know that let's work backwards. We know we have atmospheric pressure once the water exits. So this is once the water is in our esophagus going down into our stomach, and if we work backwards, now we're going reverse through the pump, right? So that takes away energy density. So now we're at a pressure that's lower than PATM in our mouth, which is what we said before. And then if we go down the straw back to the surface of the water, we go down into the water back to a higher pressure, back at PATM. So the mouth puts a pump, your mouth acts as a pump, and kind of creates this pressure differential between the water and your mouth. The water flows up there, and then when it goes through, it gets a lower pressure as it goes up to the mouth, and then the pump pumps it back up to atmospheric pressure. So we've fit the action of drinking through a straw to our model here. We did have to make some simplifying assumptions, and this is, this thing with ignoring kinetic energy is definitely not rigorous, but it serves to show how we can make this model useful and kind of understand something that might be a little mysterious. This isn't a problem start, as you saw from the 4 that I posted, but this is the type of thinking that I want you to take away from this class and maybe apply to those. We have this system, the problem start, I don't want it to be not like this one, it was just like, how does a straw work? I would never give you something like that. But to take something that's mainly just a physical system, a behavior, and then how do you fit the model to it? That's the work you can do outside of class. Where does our model fit into there? What points do I want to look at in between? What's changing between those two? And then on the quiz, you just have to solve. That just have to solve is oversimplifying it, but that's the idea. Okay, so let's do a clicker question. The example we're looking at here, we have a pipe with air flowing in it from left to right. There is resistance in that pipe, and there is a change in area. Then we have kind of a pressure gauge, although this isn't like what we saw before, where we have a vertical column going up with water in it, and like the water flows up. Now the air pushes down on the water, right? So the pressure in this pipe at the top is going to push down on these columns of water because there's air pressure in the tube, so the air is going to flow down and push it, and these levels will come to certain heights. So they're not equal. This is just drawn because I don't want to give away the answer, but we're going to try to find a relationship between these three heights. So there is resistance, there is a change in area. First question is, how does the water level H1 compare to the water level H3? So I'm going to open up the clicker poll and give you a minute or so for that. How does the water level 1 compare to 3? I'll give you maybe 15 more seconds. All right, I'm going to call it there. Don't worry if you don't have your answer in. Next, you can just shoot from the hip if you're running out of time, or just don't answer. Again, they're not counted. Okay, so let's work through this together before I give out the answer. So what's changing between point 1 and point 3? Potential energy, is that changing? No, right? They're at the same height, 1 and 3. So now we're not talking about the water levels. We're just talking about the air in the pipe going across the top. So this is an important thing to note, is that we have different fluid systems here, right? We have one fluid system on the top, the air, and then we have the fluid systems that are the water in the pipe. But just the top, from 1 to 3, there's no change in potential energy, right? Because they're at the same height. There's also no change in kinetic energy because they have the same area. We don't have a pump, but we do have dissipation. We have this minus IR term. So we just get our change in pressure is minus IR. So there's a decrease in pressure, right? This is negative, so that's negative. So if 3 is at a lower pressure than 1, that means that the height in 3 is going to be higher. So this is a little tricky. It's opposite of what we saw before with the standpipes, right, where a higher pressure gives you a higher water level, because now we're not pushing water up. We're not like pumping it up. We're pushing down on it, right? So since we decided the pressure at 1 is greater, the air is going to be pushing down harder on the water in 1 than it is on 3. If it's pushing down harder, the water level will be lower than it is in 3. Okay, so let's try one that's a little more tricky. What about 1 to 2? How does the height in column 1 compare to the height in column 2? I'll give you another minute for this one. And feel free to chat with your neighbors about these as well. About 10 more seconds. All right, I'm going to call it there. So this one's a little trickier. Now we have the addition of kinetic energy density changing. Right? They're still at the same height, so there's no potential energy density difference from 1 to 2. But there is a kinetic energy difference. Why? Well, our indicator for kinetic energy is the cross-sectional area of the pipe, which decreases from 1 to 2. And remember, if the area decreases, the speed increases. So kinetic energy is increasing from 1 to 2. So we still have our delta P is equal to this minus IR, but here we have an increase in kinetic energy density. So depending on how you want to think about this, you could either have, you have negative on this side. So if we have a positive here, this must be negative. In order for this side to be equal to a negative number as well, if we have a positive number here, the only way for this to work out is if the pressure change is negative. Another way to think about it is just, well, I have delta P here, negative on that side, so I'll take my positive number, move it over here, which makes it negative, so just my pressure change is a negative minus something else, right? So my pressure change is negative. So P1 is greater than P2, pressure decreases, which gives us that the height, again, in H1 is lower than H2. Remember, it's flipped, so pressure in 1 is greater, pushing down harder on the fluid in column 1, so it goes lower. In 2, the pressure is not as great as 1, so the water can go to a higher level. All right, last one. This one, now let's look at between 2 and 3. So I will give you a final minute for this one. About 10 more seconds. All right, I'm gonna call it there. Nice job with that one. So, same thing, we have both kinetic energy and dissipation, but in this case, our kinetic energy is going to decrease, right? Because we're going from a thin pipe with a higher speed to a thicker pipe with a lower speed. So our kinetic energy term is negative here. So we actually can't tell the difference between the heights. So same two types of thinking about it now. Negative on this side, negative here. So this could be a positive or a negative depending on how big either of these two things are. Or if I move this over here, I have a negative plus a positive. So we can't tell what the sign is without more information. So to sum this up, let's just assume, let's say the resistance is very small. So in that case, this change between 2 and 3, before we have the minus IR, now we moved delta KE over volume here, minus, and we said delta KE is negative, right? Going from a thin to a thick pipe, we have a drop in kinetic energy. So that's a negative negative. So we just have plus and a minus. And if we assume resistance is really small, then my pressure change between 2 and 3 will be positive, which gives me a drop in the height, right? If my pressure change is positive, pressure at 3 is greater, pressure is pushing down more on the surface of the fluid, so it is down lower. And both of those, we decided, have a lower pressure than 1. So they should have higher fluid levels. Questions about this one? This is a type of problem it's great to go over. You should be very comfortable with it, and I think it goes to reiterate that you should, unless we give them to you, I mean, feel free to ask us if, like, is this rule good? But in general, I would avoid trying to make rules like larger H means greater pressure or something like, you know, in this case, it's not like that. The lower H gives you a greater pressure because it's on the bottom. You know, each problem can be very different. So make sure you know what you're doing, and where possible, try not to use like generalizing rules, again, unless we give them to you. We'll be very clear when something is always true. Yeah. All right. So now let's start to transition toward electric circuits. So we've been talking about fluid circuits. We're going to make, well, I say circuits. First we have to transition to circuits. We've been looking at kind of sections of circuits, right? From point A to point B, what happens in between. Now we're going to connect them, make a full loop. The concept really doesn't change there, but it lets us solve for different things and learn different things about the circuit. So the change that we're making now when we have closed loops is that instead of worrying about what the pressure, potential energy density, and kinetic energy density are at any individual point, we're just going to say that the total change, delta P plus delta PE plus delta KE, around any closed loop, so starting at one point, going around, and coming back to it, is always going to be 0. And that kind of makes sense, right? If you have a point, you have a pressure, potential energy, and a kinetic. And if I take that same point, and I want to find the difference between this point and the same point, it has the same height, it has the same cross-sectional area, so the same part of the pipe, and so it's going to have the same pressure. So we're just going to collapse those things into what is called total head. That's a term I'll use a little bit here just because it's convenient for fluid circuits, but we won't really use that many fluid circuits down the road. We're mostly aiming for electric circuits. So with this lecture, I'm going to demonstrate a lot of these circuit concepts with fluids, and then when we move to electric circuits, it should click a little bit faster just because it's really the same math. Okay, so total head, it's like, now this is like our budget, right? This is how much, or our energy density that we spend and receive as we go through a circuit. Pumps add to it, and pipes with resistance take away from it. This sigma here that is just a sum. It just like means add up all the pumps and all the resistances that you have as you go throughout a circuit. So as I trace my way through, I'll go, like in this circuit here, we'll say the pipe has resistance. So I go through this pump and have an E pump, and I go through the pipe and I have a minus IR. And the key here is that our delta head, so that change in delta P plus delta PE plus delta KE, because we went in the whole loop, is 0. So that would be like starting at the point where it says like P1. If I go around back to P1, my change has to be 0. And that's equal to the sum of all the energy that I get and give away as I go through the circuit, right? I being some fluid that's flowing through the circuit. So now our total head is 0, which is equal to E pump, the energy that I get, minus IR, the energy that is dissipated by the pipe. And now with this, we can solve for the current, maybe. Right? That's going to be something that comes in a lot in electricity. What is the current? Yeah, so let's take a look at when we have resistors in series. So in this case, now we have a circuit where we have 2 sections of pipe with resistance. We'll say there's no resistance outside of these 2 sections, but here we have R1, here we have R2. So let's use our loop rule again. We'll go around from point 4 to point 5, down through here, through 1, R1, around the circuit. So if we do that, we start with 0. That's our total head when we go around the loop. And that's equal to the energy we get from the pump, E pump over volume, minus IR1, minus IR2, back to the end. So those things all have to add up to 0. Whatever I get, I have to spend, because we're in a full loop. So the thing that's really important here is that when they're in series, which just means one after the other, consecutive, like they are here, they have the same current, right? And that just follows from our continuity rule or conservation that whatever fluid flows in through here in any amount of time has to flow through here and then here and then here. There's nowhere for the water to go, right? It can't build up anywhere or leak out. So I1 equals I2 equals I3, like at each one of those points. So that's why I use the same I for each one of these resistors. And that lets me just factor it out, right? This minus IR1 minus IR2 is just equal to minus I times R1 plus R2. So we just discovered how resistances work in series, or one after the other. You just add them together. So the goal here, when I say R series, is to combine these into a single resistor, or like an effective resistance, or equivalent resistance is terms you might see. It's just, we want to know the behavior of the circuit. We don't care about all the intricacies of each different part. We just want to know like what this total current is in the circuit. So we want to break it down, or not break it down, I guess. We want to put it back together, work backwards into the most simple circuit we can with just one resistor. So we could replace these two with a single resistor that has a resistance that's R1 plus R2, and we'll get the same current in this circuit. So resistors in series, just add them together. And that we can do that because they share a current. So now let's talk about a little bit more complex of a scenario. Now we have resistors in parallel. Parallel, like shown here, well, they're parallel. You can go one or another. It's a fork, it's a junction. Whatever current flows into here gets split between I1 and I2, right? So that's where we get our, well, yeah, and kind of not exactly what I was going to say so far, but the current gets split between here. We have two loops, right? We can either go across the pump, up through here, and back, or same thing across the pump, down through this bottom, and back. Both of those are perfectly valid loops that I could follow. And so I get two loop rule equations. This total head 0, because we went in a whole loop. There can't be any change in like the total energy that the fluid has. So one way, it gains energy density from the pump, and then loses it in pipe 1, where it's R1, or it gains energy density from the pump, and then loses it across I2. In this case, like I mentioned, they do not share currents, right? Because whatever comes in through here can go either here or there, right? Not every unit of fluid that goes through here is going to also go through here. In fact, none of it will. That's impossible for it. It has to pick. So I1 and I2 have to add up to I, which is our junction rule here. We have our total current, and that's made up of the individual currents that go into the junction, right? So now we have a few equations. We have our junction rule, which tells us the conservation or continuity. And then we also have that the change in pressure across these two pieces is equal. I'm sorry, I'm going a little out of order here. But what our loop rules allowed us to solve for was the, well, kind of disjointed. Those are both valid loop rules. We can go back to the delta P, right? So this is just saying between 1 and 2, my delta P is minus IR1 for P1, 2, or minus IR2 for P1, 2. Those are both the same pressure change, right? These have to be the same because otherwise we'd have two different answers for what the pressure is at point 2. So at point 1, at the beginning of these two pipes, we clearly only have one pressure, right? We can't have, they share a point, they're in contact, and we know two fluid systems in contact share a pressure. So we have a single pressure there. And then if we go this way, we get that pressure plus some change. If we go this way, we get that pressure plus some change. Same thing applies over here. These come back into contact, and so they have to share a pressure. So if these are the same, and these are the same, the change across them has to be the same. So that's why this delta P 1, 2 has to only have one answer, even though it's equal to these two different things. So why is that possible? It's because they don't share a current. R1 and R2 are not the same, but neither are I1 and I2. What those currents are will be related to what the resistances are, right? We'll talk a little bit more about that soon, but in this case, they share a pressure drop, not a current, whereas in series, they shared a current, and when they're one after another, they have the same current. I didn't mention this, but they don't have to have the same pressure drop, right? I can have one pressure drop and then another one. There's no rule that's broken if this is a drop in 3 joules per meter cubed, and then this one is a drop of 2. We have a total of 5. There's nothing wrong with that. But if this was 3 and this was 2, then we'd have an issue. Okay, so we have a junction rule. We have that our 2 pressure drops across resistors in parallel have to be the same. So let's solve for what the equivalent resistance is here. So remember, for the case of them in series, the goal was to find what the relationship between these resistances and their equivalent resistance is. So if I want to replace these with a single resistance, what resistance is that going to be? What resistance does the whole circuit see? We want to find the behavior of it. So we want to find the same thing, except for if they are in parallel. So I'm just going to kind of not skip through it. I'll very briefly explain, but the reason I just popped this all up here is because you don't need to know it. You need to know this. This is how resistors add in parallel. The way I solved it, this is the algebra if you want to look through it, but I just took the things we already said in the previous slides. This top row is just saying that the pressure drop across 1, which is minus IR1, has to equal the pressure drop across R2, which is minus IR2. And then I also set that equal to I times this R parallel. And that just means the whole current, not I1 or I2, not those pieces of it. But if I just replaced R1 and R2 with a single resistor, I keep saying resistor like an electric circuit, but pipe with resistance we're still talking about. If I just replace that with one pipe with some resistance R parallel, then all the current would flow through it. What should that R parallel be if I want it to behave the same way as this circuit everywhere else? So that's kind of a weird thing to think about, but it'll become more clear why we want to do it. Well, we just want to simplify it, right? We want to see what the behavior is. So if we're going to replace these 2 in parallel with one equivalent pipe, with one pipe with equivalent resistance, I should say, we get this equation. And notice that it's 1 over R parallel. So once we plug in R1 and R2 here and get an answer, we have to flip it in order to get the correct R parallel. Otherwise, we'll have its inverse. So to solve it, I just use that. The junction rule, which is I1 plus I2, is equal to that total I, and it's just algebra here. Again, not responsible for this, but it is how you get this expression. There's no other information that we need to get it. Okay, and then the important part is that they share a pressure drop. So in series, they share a current. In parallel, they share a pressure drop across them. That's very important, and something very similar will happen for electric circuits. Okay. So now let's just make the transition to electric circuits. We'll go through each one of these pieces in detail as we move through. So at first, you don't have to write any of this down, but just glaze your eyes over it and just observe the similarity. Right? We have some, as far as the equation goes, we have some energy density on the left. That's like our total head. That's the thing in a loop rule that is 0 when you go all the way around. And then on the right, we have all the things that add to that energy density and take away. So it's the same thing. We just have some budget, some total energy density. We can get it from something. We can take it away. In fluid circuits, pumps give the energy density, and resistance takes it away. In electrical circuits, batteries give the energy density, and resistors take it away. Resistors work just like pipes with resistance. When the electricity flows through it, they reduce the energy density. So extremely similar. We just have to learn some new symbols and kind of a new concept. So let's define the new terms that we're using. Current, the same word, same variable I we're going to use, except anywhere we had volume, how we describe a fluid, right, like meters cubed, how much water there is, now we care about charge, which is coulombs. So the current is charge per unit time instead of volume of fluid per unit time. Current flows from positive to negative, even though electricity, so if we take a break, don't pay attention to this for a sec, we all, just thinking back to whatever physics class or just science class we took, we know that electrons are the thing that flow, right? We have nuclei and atoms that are heavy and stay relatively still, and then the electrons are the thing they pass to each other. That's how electricity flows. For some reason, there's some historical reason, but in physics we just talk about current being the flow of positive charge. That simply doesn't happen. Protons don't move through circuits, but it doesn't matter, just the flow of positive charge is the opposite of the flow of negative charge. So for our purposes in this class, current flows from plus to minus. So this way around the circuit, and current is the flow of positive charge, even though what's physically happening is the opposite. Whatever. But the way we keep track of current is how many coulombs per second. Coulombs is an amount of charge, how much of that is flowing through any given part of the circuit per second. So that's an important characteristic of any circuit, is what is the current flowing through it. And actually, let's take a look at this simulation, if it works. Oops, I'm clicking on the wrong thing. Oh, whatever. It's not working. I highly recommend, if you do take a look at the lecture slides, and you probably will see this now it wants to open. I think my computer's too slow to do it. Anyway, I recommend that you click that link and play around with it, especially later in the course, the next few DLs. It really illuminates just very basic circuits and how they flow, and you can build more complex circuits and learn stuff. But anyway, it was just illustrating that current flows from positive to negative, and electrons flow the opposite. Okay, so current, charge per unit time instead of volume per unit time. Voltage, this is our new energy density. Same thing, we're going to swap out volume, how much fluid, for charge, how much charge. Coulombs, so now instead of joules per meter cubed, we have joules per coulomb. How much energy does each unit of charge that's flowing through the circuit have? So we now have a way to quantify how much charge is flowing and how much energy does each charge have. So charge and energy are separate things. Each charge has some energy budget to spend. Right? Battery gives it, resistors take it away. So now we still have current, just different units, and now instead of pressure or energy density, we have voltage. So if you remember this equation here, I put up next to our total head equals the sum of pumps and resistors. Now we swap out total head for delta V. And there's we're not going to define potential or kinetic energy or anything like that. For charge, we just need to know, since we're using loops, just delta V, voltage drop. Okay, what is our delta? Well, same thing, it's positions. So any delta is between point A and point B, and we care about what batteries or resistors are in between point A and point B. In most cases, or many cases, we'll be talking about a full loop, and so our delta V will be 0, right? Because we're going from point A around back to point A. So yeah, delta is spatial, but for loops, it will be 0. Delta V is 0. All right, so basic elements of our circuit. We'll add a couple more of these, but we have batteries, which are this symbol up here. It's just a long line and a short line. The long line is the positive side of the battery. The short line is the negative. Sometimes you might see that doubled, just like long, short, long, short. They're both the same thing, but it's important to note that current flows from the positive, the long side of the battery, to the negative side, and then back through. So going from minus to plus, it gains energy, and then flows around from high energy to low energy. Resistors, they take away the energy, and they are this little squiggly thing, or zigzag rather, and the voltage drop across the resistor is minus II. So the voltage gain, and it's mentioned from the battery is this epsilon, for EMF. EMF is another word you'll hear instead of battery. It's electromotive force. It's just like the strength of the battery. What voltage does the battery set up and give to the charges moving around? So if I have epsilon equals 3 volts, a 3-volt battery, that means that charges that pass through it will gain 3 volts. And then they have 3 volts to spend as they go through the circuit. They'll get back to the battery, and they'll be broke, and they'll get it back, and go through. So epsilon is the voltage that electrons gain, charges gain through the battery, and then they lose minus IR, which also works out to be the voltage when they go through the resistor. The units of R are called ohms, noted by this omega here. You can look up or work out for yourself the exact units of ohms because you can break it down into like coulomb second, basic units. But you really don't need to use it in this class. For what we're dealing with, I, which is our coulombs per second, times ohms gives you a voltage, which is a joules per coulomb, energy per charge. Yeah, okay. So let's just exercise our loop rule on this very simple circuit. Let's start at point 4. So if we go from, let's look at individual voltage drops first. So just between point A and point B. From 4 to 1, our delta V is V final minus V initial, or V1 minus V4. We get epsilon. As we go across the battery from minus to plus, it pumps energy into the charges, and we come out with this epsilon, whatever voltage that is. So now we have that to spend. Now we go through the circuit. There's nothing in this wire. We'll assume it has no resistance. So there's 0 change between point 1 and point 2. Then when we go from 2 to 3, V final minus V initial gives us minus IR. We had that epsilon, and now we spend it as we go across the resistor. We lose minus IR of our voltage, and then back from 3 to 4, 0, because it's just a wire, and we're back where we started. So if we add all those things together, epsilon plus 0 minus IR plus 0 equals 0. We just get 0 is epsilon minus IR. So the loop rule shows us that in order to have, well, the loop rule be right, in order to start at one point, get back to that point, and have no change, that the amount of voltage lost of the resistor, the voltage drop across the resistor, is exactly equal to the voltage gain from the battery. Right? So in order to have that work out to be 0 when we get back to where we started, whatever we gain, we have to lose. So if I increase the voltage of the battery, I'm going to increase the voltage drop as well. So if I have a 3-volt battery, I'm going to lose 3 volts across here. If I have a 6-volt battery, I'm going to lose 6 volts across here. Now how does that work out? Because we're not changing R. R is just a resistance, it's a characteristic of the resistor. So how do we actually change the voltage drop? By just changing the battery, well, it's the current. So if you solve this loop rule up here, just move IR to the other side, divide by R, our current is equal to the voltage of the battery divided by R. So if we increase the strength of the battery, increase epsilon, we increase the current. And if the current is larger, then minus IR is larger, right? Because we increase the current. So increasing the battery size increases the current, which increases the voltage drop. So it all will work out. So let's do a couple practice questions with these. So same circuit here. What happens to the current if epsilon, the voltage of the battery, is doubled? Try to keep this one to just 30 seconds or so. Five more seconds. All right, I'm going to call it there. So, nice job on that one. If the current is if the voltage of the battery is doubled, the current will double. Remember, we have from our loop rule, like you don't necessarily need to solve this out every time, kind of recommend it, but our I is just the voltage of the battery over the resistance. So if we double that, we double that, right? If we give the electrons or charges more energy, then the current will be doubled. Okay. What will happen to the current if the resistance is doubled? Let's try that. So now battery stays the same strength, but our resistance is doubled. Ten more seconds. All right. Yeah, also nice job with that one. If we double the resistance, the current will reduce to half. So if we make it harder for the charge to flow through the circuit, harder for the current to make it through, we'll have a lower current. And that works out here. If we increase the strength of the battery, we need a larger current to have the same voltage drop and have this equation work out. And if we increase the resistance, we have to decrease the current in order to have the same voltage drop. So it all kind of works out. I like to use the analogy of like trying to send a large group of people through a small hallway, right? If we push harder, then they're all bumping into each other, right? Super crowded, trying to shove a big group of people through a hallway. If we push harder, in other words, if we have a stronger battery, then there will be more resistance, or sorry, there will be a larger voltage drop, or in other words, they'll bump into each other more, and it will be harder for them to get through, right? If I just really shove these people through the hallway, they'll all bump into each other a ton, and they'll lose a bunch of energy as they go through. But and same thing, if I double the resistance, or like make the hallway more narrow, then it will slow them down. Less people will get through. So it wasn't super clear there. I think the hallway analogy works out better for something I'm about to use later, but maybe it helps. So increasing battery voltage will increase the current. Increasing resistance will decrease the current. Okay, so now let's look at series versus parallel resistors. So what took a lot of time before to just kind of work through how do we deal with pipes that have resistance in series and pipes that are in parallel, it works the exact same way as resistors. In fact, the variable is the same too. Each pipe with resistance has some value R, some resistance. Same thing for a resistor. Except now instead of fluid flowing through a pipe, it's charge flowing through a circuit. So if we have two resistors in series, or one after another, then the equivalent resistance is just R1 plus R2. Just add them together. So if I wanted to replace these with a single resistor and still have the circuit behave the same way, in other words, still have the same current, then I would that resistor, that REQ, our equivalent, or R series that I had before, is just the sum. But if I have them in parallel, now the current can go through either or. So now instead of I1, I2, and I all being equal, because all the current has to go through everywhere, the current can pick R1 or R2 to go through. So I1 and I2 are both pieces of I, and they have to add up to get I. And from that, also knowing now we said the pressure drop, if this was a pipe, the pressure drop across these two pipes has to be the same for consistency, right? Whatever the pressure here has to be the pressure there. You know, just because you have a single point, it can't have multiple pressures. The same thing goes for the voltage here. Whatever the voltage drop across R1 has to be the voltage drop across R2. I1 and R1 don't have to equal R2 and I2 and R2 individually, but I1, R1 has to equal I2, R2 in order to get one voltage answer there and one voltage answer there. And using all that, we can do the same exact math that's on the other slide with the same R's, same everything, and the equivalent resistance is, well, 1 over the equivalent resistance is 1 over R1 plus 1 over R2. So what is my next slide here? Yeah, so let's do this quick question first before we get into more math. So we have two 3 ohm resistors. So that's just their resistance. And we're going to put them in either parallel or series. So this is 3 ohms, that's 3 ohms, or this is 3 ohms, that's 3 ohms. So I'm going to say that in parallel, they'll have a greater R equivalent than they will in series. Is that true or false? So I'll give you a sec to, well, I'll give you a little bit. Work on that. See if you can find the R equivalent for each one and see what is larger. I'll give you about 15 more seconds with this one. All right, so the answer is, well, let's work it out together first. Right, so I didn't have these labeled just so you could kind of exercise your memory there. But the first equation is for series. That's just one after another. In that case, the equivalent resistance is just adding them together. So it's R equivalent is 3 ohms plus 3 ohms. And we get 6 ohms. So in series, 6 ohms is just 2 3 ohm resistors next to each other. But in parallel, if we have a circuit where you can leave the battery and go through one of the 3 ohm resistors, either or, then we add them together like this. So we get 1 over Req is 1 over 3 ohms plus 1 over 3 ohms. So we get 2/3, and this shouldn't be ohms, this should be 1 over ohms. So that's my mistake there. But so we have to flip that to get the actual Req, because that's 1 over Req. So we get 3/2 ohms for parallel. So the answer is false. The equivalent resistance for resistors, the same resistors in parallel, is going to be less than the equivalent resistance of resistors in series. Let's think about why that is intuitively. So if they're in series, let's go back to here. If they're in series, if we go around and then through R1, right? So first, when we leave the battery, charge has this voltage epsilon, right? We just got the voltage from the battery. This is our energy density to spend. We go through the circuit, we spend some on R1, and then once we did all that work, made it through R1, we have to go through R2. We have no other choice. So again, we have to go through R2 and spend the rest of our energy density until we go back up to the battery and re-up and go back around the circuit. But there's no choice but to go through R1 and R2. So every single charge that goes through here encounters both. 3 ohms, then 3 ohms. So we get a larger resistance. In fact, just the sum of those two, because every charge has to go through both. Parallel, it's a little more complicated, because I'm going to start with saying that the equivalent resistance for resistors in parallel will always be lower than the lowest resistance of the resistors that are in parallel. So if R1 is 1 ohm and R2 is 3 million ohms, then the equivalent resistance is going to be less than 1 ohm. Maybe only very little bit, but since 1 ohm is the smallest resistance of those two, the equivalent resistance has to be even smaller than that if they're in parallel. Let's think about the reason why. All right, here's a clearer way than my hallway analogy before that I feel like it didn't work that well. Imagine you have a tunnel going through a mountain, right? If you have, and trying to get people to go through it. If you only give them the option of the tunnel, then they're all going to have to cram through the tunnel, and they'll get super crowded, and it'll be tough for them to get through. That's our series example. It just can only go through one route, through both resistors, or through this long crowded tunnel. But let's say you also open up a path that goes up and over the mountain. So in that case, the tunnel is R1. That's just 1 ohm. It's super easy. You just walk through the tunnel. And R2 is the choice of going over the mountain. That's the 3 million ohms. It's much, much harder, but you can do that instead of the tunnel. There's no reason not to. Well, it's much harder, but there's nothing preventing you from doing it. So if you send a huge group of people through there, most of them are going to pick the tunnel, right? Because it's much easier. But a few will go over the mountain. A few intrepid people will decide, I want to get some exercise, I'm going to go over it. Same thing in the circuit. A few intrepid electrons will decide, I'm going to go through the 3 million ohm resistor, even though the other one's much easier. There's no one there, maybe they don't like crowds, whatever, they're going to go through R2. What that ends up doing is lightening the load on R1, right? So R1 was 1 ohm. If we had only R1, the equivalent resistance is just 1 ohm. But now we have R1, and we give another path through R2, which is 3 million. Even though the 3 million is super difficult, all it did was lighten the load ever so slightly on R1, right? We gave another option. So some of the charge can go another way, and so R1 will be less crowded, and it will be easier to get through. So our overall resistance will be lower than R1. You can use the same logic with any big group of resistors. That if I added another one, if I had 50 resistors, and whatever the lowest one is, just think of start there, that's my circuit through that resistor, and then all the other ones just add options. So it's impossible for the total resistance or the equivalent resistance to be any bigger than that. Because at the very least, we're just giving a couple electrons another place to go. In the case of the 3 ohm resistors, we got 3 halves. So we got half of the resistance from putting them in parallel. Not just slightly less than 3, but halved it. That's because they're both equal, right? So now only half the amount of electrons have to go through each one. If the resistances are equal, there's going to be no preferred resistor. And exactly half will go through one, half will go through the other, so they see the whole circuit sees half the resistance equivalently. You'll see this a lot more in DL. I know I'm saying a lot without putting a lot on the board, but you'll see a lot more of these problems in DL. If you have, when they're not equal, when the two resistors are not equal, the current will favor the lower resistance, right? Just the same way if the mountain versus the tunnel, 1 ohm versus 3 million, most of the current will go through the 1 ohm. Most of the people will go through the tunnel. But if you had 2 bridges side by side that are perfectly flat, it'll be split half and half. So anything in between, that logic still applies. The more difficult path, the higher resistance will see less current. Yeah? Yeah, definitely. So you would, let's say I know what my resistance is, and then I also, the third thing involved in that equation is the current. So like super simple, we just have our current is our voltage of the battery divided by the resistance. So let's say we have a light bulb with some resistance, R, right? And I want to light up a room. And I need a certain amount of current through that light bulb. That's the amount of charge flowing through it. This actually leads really well into what we're doing next. I need a certain amount of light, right? So that's I'll explain soon why that is, but more current gives me more light through the light bulb. More charge passing through it gives me more light. So if I know its resistance, and I know the needed current, then that gives me what size battery I need. Because a smaller battery will give me a smaller current. That might not be enough. And so I might have to up the size of the battery in order to get the same brightness out of that resistor. Yeah, good point. Okay. So power dissipation. Power, first let's talk about what it is. Its units are energy per unit time. So that's how much energy is entering or leaving the system in any given amount of time, right? So how do we get it? Well, we have energy per charge, which is our voltage, and we have our charge per time that's flowing through the circuit, which is our current, So if we multiply those two, charge cancels out, and we just get energy per time. Right? So if we take our voltage drop across any, or voltage gain, or voltage change across any part of the circuit, and multiply it by the current through it, we'll get the power dissipated by that element. We're not really going to do this, but the same thing works in fluid circuits, right? Our units are going to be different, energy per volume and volume per time, but they still cancel just the same and get energy per time. So a pipe with resistance will dissipate energy, and a pump will add energy to the circuit. So the two things, the voltage drop, something that takes energy away, are like light bulbs and resistors. You can think of light bulbs as resistors as just like giving a physical, purpose for it. Resistors heat up when we put them in circuits, right? So thermal energy is created, just like when fluid flows through a rusty pipe. There's friction, and some of the energy is dissipated, turns to thermal. Same thing happens to a resistor or a light bulb. It's very obvious to see. If the light bulbs light up, they're emitting electromagnetic waves. So light energy is leaving it. You can see it, and so there must be some sort of energy dissipation if you have an illuminated light bulb or a resistor connected. Batteries give energy to the circuit, so you can see there's a voltage increase across the battery. That's why we put them there, to pump energy into a circuit. So if we have two of these elements in any given circuit, we have a battery, something that gives the energy, and then something that takes away from it, then the rate at which the battery pumps energy into the circuit, the energy per time that it pumps in, must be equal to the energy per time that whatever the resistor, the light bulb, is taking out of it. So we have that energy conservation. We could think real quick, what happens if we just had a battery with a wire connecting it, like no resistance? And so then we have an increase in voltage from the battery, and then it goes around and just comes back to it. So I wish I had a visual for this, but what's happening there? Well, saying there's no resistance is not really physical. Like every wire, no matter what it's made out of, has some bit of resistance. So if we had a battery connected to a wire with super low resistance, we would just have a huge current. That's what's called a short circuit. You'll see a lot more of this in DL. But anyway, we have things that dissipate and things that add energy. And to get what that power is, that energy per time, we just multiply the voltage and the current. So for a battery, that's pretty easy. The voltage is just this epsilon. That's just a number, a characteristic of the battery in volts, times the current. For a resistor, there's a few expressions here. They're all equivalent to each other. So using these will all give the same answer. But to see where we got them, this first expression is super similar to this one. This is just our current times the voltage drop across the resistor. Right? So we want the voltage times the current to get the power dissipation. So this is minus IR, or really the absolute value. Because we can talk about, we normally just talk about like power dissipated or gained. We're not really going to assign signs to them and add and subtract. So we'll just say power is always positive for these purposes. But anyway, our delta V is IR. So if our power is I times IR, it's just equal to I squared R. This last equation is also true. I'll let you work that one out on your own. I'm not sure if you do in DL, but that could be a fun exercise. Fun. But they're all equal to each other. Which one you use when you're solving a problem is just convenience, I guess. If you already have I and R, I would probably use the middle one. If you have I and delta V, use this one, etc. But you could always, from this, solve for delta V, so on and so forth. They're all saying the same thing. So that's power added to the circuit from the battery, power dissipated from the resistor. So let's go through a quick example of power dissipation with a circuit with either one or two light bulbs in it. So first, let's look at one light bulb, just a battery and a light bulb. I put R there because that's the symbol that we'll use for light bulbs usually, but they just act the same way as a resistor. They have some resistance, and they transfer the energy from the electricity, the voltage, into thermal energy. So let's do our loop rule. Go across the battery, we get epsilon, and then across the light bulb, we get the minus IR. And that has to add up to 0 because it's a loop. So that lets us solve, as we did before for the current, is just epsilon over r. Very specifically what I did, just add IR over here, divide by R. So that gives us the current. And just a quick note on this, when we were finding R equivalent for these circuits, what I mean by R, when I say like we want a resistor that would give the same behavior as this group of resistors that we're like turning them into, like let's say we wanted to turn this circuit with 2 light bulbs into an equivalent circuit with just 1, and have this R value be whatever equivalent we would have from these 2. It just means having the same current come out of the battery. So here, this is our current coming out of the battery, and it's just equal to the voltage across it divided by the resistance that it sees, right? So let's see what that, well, first we can just finish solving this one real quick. What that tells us is that the power, let's use I squared R because we have both of these things, turns out to this epsilon squared over R. That's not something you need to memorize. You should always just plug in from one of the expressions for power, but it just shows us how we would find the power dissipated for the light bulb. But now if we look at the parallel one, I have this REQ, my equivalent resistance. So that would mean if I took, like I said, if I took these 2 light bulbs in parallel and used that equivalent resistance expression to find this REQ, what it means is if I simplify this to a circuit that looks just like this, my current would be, I want my current to be the same. So what resistance do I have to give one light bulb in order for it to have the same current out of the battery as this one? And it's important to note that that current is the current leaving the battery. So just along this top piece, flowing out of the battery. Because it's not the same as the current in each of the 2 branches, right? That current splits up between those 2 branches. Some goes to the top light bulb, some goes to the bottom. But if we simplify it to 1, it's the same current everywhere. So when you're simplifying parallel resistors, you kind of have to work like forwards and backwards and forwards, however you want to think about it. You first want to decompose it or kind of compose it back from this messy circuit with multiple resistors into something simple. And then once you have that something simple, that total current, then you can go and find out how it splits up in the real circuit. So the current coming out of this one would be the same as the current coming out of this one if this resistor had REQ, but it's split up between those 2 branches. I don't know, that was a lot of words and not a lot of putting stuff on the board, but this is something that you'll work with a lot in DL, and it'll be introduced a bit more slowly there. So if you solve this equation, just saying both of these light bulbs have a resistance R, we get our equivalent resistance is less than that. It's half, right? Because we give it 2 options instead of 1. And so our current is just I epsilon over REQ. So we get twice the current. And if you solve for the power, we get 4 times the power is dissipated in this circuit. So because we have 2 light bulbs here, in parallel, we split it, more current can flow through, and we get more power dissipated in this circuit. Okay. Any questions? Then I will see you next week. Remember, we have our quiz next week. Starts promptly at 9. Most of this is not on the quiz. The quiz ends with Bernoullis equation and continuity. So pretty much just this and the first couple slides, or a bunch of slides in the lecture.
Is this a valid one? They pressure